Hello, and this time talking about inverse proportion and doing it with the formula method. Now, I have previously made a direct proportion by writing out a formula video, and if you haven't seen that, it might be useful to see how it works with direct proportion first. You don't have to, it's still, relatively logical for inverse proportion. But first of all, what is inverse proportion? Well, if you know what direct proportion is, you know that direct proportion is a nice straight line graph, and it's proportional because if you make one of these two variables twice as big, then the other gets twice as big. Or if you make it 1.5 times bigger, the other gets 1.5 times bigger as well. And that's direct proportion, so they're both growing at the same rate by the same factor, timesing by the same amounts. With inverse proportion, it works differently. If you have twice as many things of one variable, you have half as many in the other. So it kind of like has an opposite effect. You double one, you half the other. 1.5 times bigger, 1.5 times smaller. And a lot of people think, well, that would make a straight line down this way, but it doesn't. It actually makes a curve like this. And that's because you've essentially got a reciprocal relationship. You're saying that y, if it's inversely proportional to x, equals some coefficient, some value, divided by x. Okay, so as one thing doubles, the other is getting half the size because of this division relationship. So that's what inverse proportion is. One thing gets bigger as one thing gets smaller. So a good example is the number of mistakes you make compared to how much you practice. So if this is practice and this is mistakes, then you would hope anyway that if you do more practice, then the number of mistakes will come down. Okay. Now I'm not saying that is definitely an inverse proportion that is consistent, so that if you do twice as much practice, you get half the many mistakes, and if you do 10 times, then 1/10 of the mistakes. And of course, what happens to the point where you get no mistakes? That would technically, in this relationship, require infinite practice, but in reality, you could get to the stage, depending on what it is, where you don't make any mistakes in a piece of music or whatever it is. So the example sort of breaks down. I think all of the actual relationships that you might look at, it will only work in a certain range, and after that, it stops being this same graph that represents it. As I say, you can't go down to zero on this. You'll never get there because it requires infinite practice. So yes, anyway, let's have a look at some of the examples and see how we actually process these things. The cost of this person's electricity bill, C, varies inversely, so it's inversely proportional, with the temperature, T. So what we can say is C is some value divided by T. It's an inverse relationship, so we have that divide. If the bill is $200 when the temperature is 25, find a formula. Well, I've almost got the formula here. I just need to know what K is. So if the bill is 200 and the temperature is 25, okay, then rearrange that. We're going to multiply by 25 and get rid of it there. So K is 200 times 25, which I presume we times that by 2 is going to be 50, so 5,000. Okay, so the formula that they want is C equals 5,000 divided by T. So just erase this. Obviously, you wouldn't in an exam, but you'd have more space in an exam. Don't destroy your working out. The bill. What's the bill when the temperature is 18? Well, now we've found the formula, we can just use it. We have now a relationship between cost and temperature. So for part B, the cost is going to be 5,000 divided by 18. I'm going to reach for the calculator for this one. 5,000 divided by 18 is, as a decimal, 27778. Okay, because it's money. Whoops, that's a 2, not a 7. 27778. Because it's money, it's dollars, then round it to the nearest cent. And if it was pounds, to the nearest penny. Okay, and the temperature generating bill of 400, well, we just substitute it into here as well, but we just need to do a bit of rearranging. 400 equals, 5,000 over t, bring the t up, and divide the 400 down, so t is 5,000 divided by 400, which I should be able to do in my head, but I'm tired, so I'm going to reach for the calculator, and the answer is 12.5 degrees. Okay, make sure you do put your units on, so degrees for this one and dollars for this one. And that's it. Once you've found that formula, I think that's what people find the hardest. They they sort of do the divide wrong. When we put the 225 in, they go, oh, well, 200 divided by 25, well, that goes in 8 times, well, that must be 8. When they forget that, it's a big number. When you divide by 25, you still get 200, so it's a much bigger number. So just be careful on that. As long as you get k right, then it's just using that formula, substituting and solving. Now, this is a much harder question, but it's only harder because of the way that it poses it. It sort of like tries to confuse you with where the numbers are. So let's have a look. The time for a pendulum to swing is inversely proportional to the square root. So you got to spot that. A lot of people don't go, oh, t is inversely to g, and they'll just say t equals k over g. But it's not, because it says the square root of the acceleration due to gravity. So you've got to put that in as well. On Earth, g is 9.8, but on the moon, find the time of a swing on the moon of a pendulum when the time that it takes to swing on Earth is 2 seconds. So they've kind of like separated it. But here we go. On Earth, we've got 2 values, so we can put those in. So 2 seconds for t equals k over root 9.8, which means that k equals, and again, I'm going to use the calculator for this, 2 times root 9.8, or 6.26, I think we'll round that as 6.26. Now, really, I should use the absolute value. There's no reason why I couldn't use the formula with these square roots in. There's nothing wrong with that at all. In a GCSE exam, you're probably okay rounding it there. Probably unlikely to give you something that gives you an unpleasant k for that very reason, because it just brings in an extra element. So excuse me using the rounded value, but of course you could put 14 root 5 over 5. Absolutely fine if you wanted to do that, and it's the more proper thing to do. So obviously you wouldn't destroy your working out, but I need the space, so I'm going to get rid of mine. And then it says, so that's not actually answered anything yet. We needed to do that to get the formula. And now it says, find the time of the swing on the moon. Well, that means what is t when g is 1.9? So t is 6.26 divided by root 1.9. And we can just put this in the calculator. Now, actually, I say that, I've written it down rounded, but there's nothing to stop me using that value. That's my answer, my previous answer. So if I want to know that, I can just say fraction of answer over root 1.9. And then I know that there's no rounding error in my answer because I've used the absolute exact answer there. And this time I feel it's legitimate rounding it because they want to know the time. So we'll give it to them in a decimal. And so this is 4.54 seconds, and we ought to also say that we've rounded it to 3 significant figures. So absolutely no different, but because it's in a context and they haven't structured it out saying formula, then this, and this, and they've separated those values, it can confuse people. But it's the same thing. It tells you how it's related, inversely proportional. Watch out for those bonus words like square or cube or square root to make sure you put those in. Plug in your 2 values that are connected to work out k and get your formula, and then you can use the value you're given to work out the thing you want. If you have any questions, then pop them down in the comments. Otherwise, ta-ra for now.